Welcome students. Myself Abhishek, Assistant Professor, J.C. Bose University of Science and Technology, YMCA Faridabad. I am going to deliver a lecture on some basic concepts of real analysis. Let us start with the basic algebraic properties of real analysis. On the set R of real numbers, there are two binary operations called addition and multiplication, denoted by plus and dot respectively. These operations satisfy the following properties. First one is commutative property under addition, that is a plus b is equals to b plus a for all a and b belongs to R. Second property is associative property under addition, that is addition of a plus b with respect to c is equals to addition of a plus addition of b plus c for all a, b and c belongs to R. Our third property is existence of an additive identity, that is there exists an element 0 belongs to R such that a plus 0 is equals to a plus 0 for all a belongs to R. Our next property is existence of an additive inverse, that is for each a in R there exists an element minus a belongs to R such that a plus minus a is equals to 0 is equals to minus a plus a. Our next property is commutative property under addition, that is a dot b is equals to b dot a for all a and b belongs to R. Our next property is associative property under multiplication, that is a dot b into c is equals to a into b dot c for all a, b and c belongs to R. Now, next property is existence of an multiplicative identity, that is there exists an element 1 in R distinct from 0 such that a into 1 is equals to a is equals to 1 into a for all a belongs to R. Next property is existence of multiplicative inverse, that is for each 0 not equals to a, that is non-zero element in real numbers, there exists an element 1 upon a belongs to R such that a into 1 upon a is equals to 1 is equals to 1 upon a into a. Now, next property is distributive property of multiplication over addition, that is multiplication of a over b plus c is equals to a dot b plus a dot c for all a, b and c belongs to R. And in similar way, we can say that b plus c into a is equals to b into a plus c into a for all a, b and c belongs to R. So, these are our algebraic properties of R. Let us start with some basic results. So, our first theorem is if z and a are any real numbers with the property z plus a is equals to a, then z must be equals to 0. Let us start with the proof. As given z and a are any real numbers with the given property z plus a is equals to a. Say this is our equation number 1. So, by the existence of additive identity property, we can say that z can be written as z is equals to z plus 0. Say this is our equation number 2. Again, by the existence of additive inverse property, for any real number, there must exist a real number minus a such that a plus minus a is equals to 0. Say this is our equation number 3. Now, substitute the value of equation number 3 in equation number 2, we get z is equals to z plus 0 plus minus a. This is our equation number 4. Now, again by the associative property under addition, equation number 4 can be written as z is equals to z plus a plus minus a. So, this is our equation number 5. Now, substitute the given condition, that is equation number 1, which is equals to z is equals to a plus minus a. Hence, we get our desired result, that is z is equals to 0. Now, moving towards our next theorem, our statement is if u and any non-zero element b in real numbers with the property u into b is equals to b, then we must have u must be equals to 0. So, moving towards the proof, as given u and non-zero b be any real numbers such that u into b is equals to b. Say this is our equation number 1. So, by the existence of multiplicative inverse property for any non-zero real number, we must have b into 1 upon b is equals to 1. Say this is our equation number 2. Again, for any real number u, there must exist a multiplicative identity such that u is equals to u into 1. Say this is our equation number 3. Now, substitute the value of equation number 2 in equation number 3. What we get? We get u is equals to u into b into 1 upon b. That is equation number 4. So, by the associative property under multiplication, equation number 4 can be rewritten as u is equals to u into b into 1 upon b. This is our equation number 5th. Now, substitute the value of equation number 1 in equation number 5th, we get u is equals to b into 1 upon b, where given as b is any non-zero real number. This implies that u must be equals to 1 as our desired results. Now, next theorem is if a be any real number, then a into 0 must be equals to 0. Proof: as given a be any real number, so by the property of multiplicative identity, we can have our equation number 1, that is a must be equals to a into 1. Now, consider the equation a plus a into 0. Using equation number 1, this can be rewritten as a plus a into 0 is equals to a into 1 plus a into 0. Then, by the distributive property of multiplication over addition, we get a plus 0 is equals to a into 1 plus 0. Say this is our equation number 2. By the property of existence of additive identity, equation number 2 can be written as a plus a into 0 is equals to a into 1. Now, substitute the value of equation number 1 in equation number 3, we get a plus a into 0 is equals to a. That implies a is equals to 0. Now, our second definition is order properties of real numbers. There is a non-empty subset P of real numbers R called the set of positive real numbers that satisfies the following properties. First property is if a and b belongs to the set P, then a plus b also belongs to that set. Second property is if a and b belongs to the set P, then their multiplication also belongs to the set P. Now, the third property is trichotomy property. Trichotomy property says that if a be any real number, then exactly one of the following conditions hold. First condition is a belongs to P, second condition is a is equals to 0, or third condition is minus a belongs to P. This is called our trichotomy property of real numbers. Next definition is let P be the non-empty subset of real numbers R called the set of positive real numbers. Then for any real number a and b, we have first if a minus b belongs to P, then we write either a is greater than b or b is less than a. In second part, if a minus b belongs to P union singleton 0, then we write either a is less greater than or equals to b or b is less or equals to a. Now, let us start with some basic theorems related to order properties of real numbers. Our first theorem is, let a, b and c be any real numbers, and if a is greater than b and b is greater than c, then we must have a is greater than c. As given in statement as a is greater than b and b is greater than c. This implies by the previous definition we can say that a minus b belongs to p and b minus c belongs to p. So, by the order properties of real numbers, we can say that their addition is also in the set P. That means a minus b plus b minus c also belongs to the set P. That implies a minus c belongs to P. Hence, by the definition, we can say that a must be greater than c. Moving towards the next theorem, our statement is, let a, b and c be any real number, and if a is greater than b, then a plus c must be greater than b plus c for any real number c. As given in the statement, a is greater than b, then by the definition we can say that a minus b belongs to the set P, where P is our set of positive real numbers. Say this is our equation number 1. As C be any real number, then there must exist an additive inverse such that C plus minus C is equals to 0. Say this is our equation number 2. Now, consider the equation a minus b. As we know, a is a real number, b is also a real number, then a minus b again forms a real number. So, if a minus b forms a real number, then there must exist some additive identity. So, we can write our equation as a minus b is equals to a minus b plus 0. Now, from the equation number 2, as we have c plus minus c is equals to 0, we can substitute the value of 0. So, our equation becomes a minus b is equals to a plus c minus b plus c. So, we can easily check a minus b belongs to the P, where P is our set of positive real numbers. So, right hand side must also belongs to the set P. That implies a plus c minus b plus c belongs to set P. That implies a plus c must be greater than b plus c. Moving towards our next theorem, statement is, let a, b and c be any real numbers if a is greater than b and c is strictly greater than 0, then we must have c times a greater than c times b. Let us start with the proof. As given, a is greater than b and c is strictly greater than 0, that implies by the definition a minus b belongs to the set P and c belongs to the set P, where P is our set of positive real numbers. Say this is our equation number 1. Then by the order properties of real numbers, we can say that c times a minus b also belongs to the set P. So, by the distributive property of multiplication over addition, we get c times a minus c times b also belongs to the set P. Hence, again by the definition, we can say that c times a is greater than c times b. Now, let us start with the next topic, absolute value and the real line. Let us start with the basic definition of absolute value. The absolute value of a real number a denoted by modulus of a, and it is defined by modulus of a is equals to a if a is strictly greater than 0, modulus of a is equals to 0 if a is equals to 0, and modulus of a is equals to minus a if a is less than 0. Geometrical interpretation of absolute value. The absolute value gives the distance between two real numbers. That is, for any real numbers a and b, the distance between a and b is modulus of a minus b. This is geometric interpretation of absolute value. Now, let us begin with some basic properties of absolute value. First one is non-negativity. That means modulus of x must be greater than or equals to 0 for all x belongs to R, where R is our set of all real numbers. And if modulus of x is equals to 0, this is only possible when x must be equals to 0, that is mod of x is equals to 0 if and only if x must be equals to 0. Moving towards next property, our next property is multiplicativity. That means modulus of x into y is equals to modulus of x into modulus of y for all x and y belongs to the set of real numbers. Moving towards next property, our next property is division rule, given that y is any non-zero real number. That means modulus of x upon y is equals to modulus of x upon modulus of y for all x and y belongs to R. Now, we have some useful results related to absolute value. First result is, for all a belongs to R, we have modulus of a square must be equals to a square. Second result is, if c is greater than or equals to 0, then modulus of c is less or equals to c if and only if a lies between minus c and c, that is minus c is less or equals to a and a is less or equals to c. Our third result is, for all a belongs to R, we have modulus of a less or equals to a and less or equals to modulus of a. That means our a lies between negative of modulus of a and positive of modulus of a. Let us start with our very first theorem, triangular inequality. Triangular inequality states that for all real numbers x, y, we can say that modulus of x plus y is less or equals to modulus of x plus modulus of y. This is our triangular inequality. Let us start with the proof. We know that for any real number a lies between negative of modulus of a and positive of modulus of a. That is, negative of modulus of a is less or equals to a and a is less or equals to modulus of a. Applying this to both the real numbers x and y, we get our equation number 1 as well as equation number 2. Our equation number 1 is modulus of negative of modulus of x is less or equals to x and x is less or equals to modulus of x. Our second equation is negative of modulus of y is less or equals to y and y is less or equals to modulus of y. Now, add these two inequalities, we get negative of modulus of x plus negative of modulus of y is less or equals to x plus y and x plus y is less or equals to modulus of x plus modulus of y. This gives negative of modulus of x plus modulus of y less or equals to x plus y and x plus y is less or equals to modulus of x plus modulus of y. Then by the definition of absolute value, we get our desired result, that is modulus of x plus y is less or equals to modulus of x plus modulus of y. A straightforward application of mathematical induction extends the triangular inequality to any finite number of elements of real numbers. That is, in terms of corollary, we can say that if a1, a2, a3 up to an are any real numbers, then modulus of a1 plus a2 plus a3 up to an is less or equals to modulus of a1 plus modulus of a2 plus modulus of a3 plus up to modulus of an. Let us start with some basic theorems related to the absolute value. Our first theorem is, let A and B are any real numbers, then we have modulus of mod A minus mod B is less or equals to modulus of A minus B. Proof: as given, A and B are real numbers. So, by the property of existence of additive inverse, we get our equation number 1, that is A plus minus A is equals to 0 and B plus minus B is equals to 0. Now, consider the equation A. As A belongs to real number R, so there must exist an additive identity for A, that implies A can be written as A is equals to A plus 0. Now, using our previous equation, we can say that A is equals to A plus B plus minus C. Now, by the distributive property of real numbers under addition, we can write as A is equals to A minus B plus B. By triangular inequality, we have modulus of A is equals to modulus of A minus B plus B is less or equals to modulus of A minus B plus modulus of B. Subtracting modulus of B both these sides, we get our equation number 2, that is modulus of A minus modulus of B is less or equals to modulus of A minus B. Now, consider in a similar way, as B is equals to B plus 0, 0 exists by the property of existence of an additive identity. Again, from equation number 1, we can substitute the value of 0. So, our equation becomes B is equals to B plus A plus minus A. Applying the distributive property, again we get B is equals to B minus A plus A. Now, using triangular inequality, we have modulus of B is equals to modulus of B minus A plus A is less or equals to modulus of B minus A plus modulus of A. Now, subtracting modulus of A both these sides, we get modulus of B minus modulus of A less or equals to modulus of A minus B, or if we rewrite this, we can write as minus of mod of B minus A is less or equals to mod of A minus mod of B. Say this is our equation number 3. Combining equation number 2 and equation number 3, we get negative of modulus of B minus A is less or equals to modulus of A minus modulus of B, and modulus of A minus modulus of B is further less or equals to modulus of A minus B. Hence, we get our desired result, that is modulus of mod A minus mod B is less or equals to modulus of A minus B. Now, moving towards our next theorem. Statement for the next theorem is, let A and B are any two real numbers, then modulus of A minus B is less or equals to modulus of A plus modulus of B. Let us start with the proof. By triangular inequality, we have for all real numbers A and B, we can write our equation number 1. Equation number 1 is modulus of A plus B is less or equals to modulus of A plus modulus of B. Now, replace B by minus B in equation 1, we get modulus of A plus minus B is less or equals to modulus of A plus modulus of minus B. So, say this is equation number 2. Since we know that modulus of minus B is nothing but modulus of B, hence modulus of A minus B less or equals to modulus of A plus modulus of B. Our definition is epsilon neighborhood. Epsilon neighborhood is defined as, for any real number A and for every epsilon greater than 0, there exists epsilon neighborhood of A is V epsilon with respect to A is equals to x belongs to R such that modulus of x minus A is less than epsilon. Further, we will discuss in next lecture. Thank you.